Now, the center of some galaxies emit abnormally large amounts of energy from a very tiny region in their core, and the emitted radiation usually fluctuates. In many instances, intense radio emission and other activity exists well outside the galaxy that come from these cores. Centers of active galaxies are referred to as AGN, active galactic nuclei. 10% of all galaxies we see are active. And of the active galaxies, we have three overlapping classes. We have radio galaxies, Seyfert galaxies, and quasars. Radio galaxies are typically elliptical galaxies, and they emit radio energy, and that energy comes from the core and regions symmetrically located outside the galaxy. The outside regions are called radio lobes, and they may span hundreds of millions of light years. And the core itself may be less than a light month across, as opposed to the size of a galaxy, which could be 50,000 light years across. And these lobes can actually be swept back as this galaxy in the center is moving through the universe, and the material out here interacts with the intergalactic dust and matter that's out there, similar to what we have between stars, and so it's swept back. Now, the energy in these is as much as 1,000,000 times more than a normal galaxy. The radio emission is synchrotron radiation. High-speed electrons are generated in the core and shoot out via jets in the direction of the lobes. These high-speed electrons eventually collide with surrounding gas and spread out to form lobes. In this radio galaxy, this little white dot in the center is the galaxy. The lobes, which are much bigger than the galaxy, come out symmetrically from each side. Now, Seyfert galaxies are spiral galaxies with abnormally luminous nucleus. The nucleus can actually put out as much energy as the Milky Way. So, an entire galactic amount of light coming from a very small region in the center. That region of emission is less than a light year across, and the wavelength of these light emissions range from the infrared to X-rays, and it fluctuates rapidly, sometimes changing in just a few minutes. They also contain gas clouds moving at high speeds, and occasionally the gas is ejected in small jets. So we have rapidly moving gas and small bright nucleus make Seyfert galaxies similar to radio galaxies, and in fact, some Seyfert galaxies are radio galaxies as well. And the last of these are quasars. Quasars have the largest redshift of any astronomical object. So if the largest redshift means they're moving faster away from us than anything else. And Hubble's law then implies that they are the furthest distances from us, as much as 10 billion light years away. To be visible at those distances, they must be 1,000 times or more luminous than the entire Milky Way. Now, there are some that are similar to radio galaxies in emissions. Others are similar to radio and Seyfert galaxies in that they eject hot gas from the centers. And we have superluminal motion in the jets indicate extreme high-speed motions. Recent images reveal quasars often lie in faint, fuzzy-looking objects that appear to be ordinary galaxies. Based on the output fluctuations, quasars resemble the AGNs of radio galaxies and Seyfert galaxies in that they're small, say fractions of a light year across in some cases. Now this leads us to another way of determining the diameter of an astronomical object, just using light variability. This is going to use three assumptions. The rate at which light is emitted from an active region is the same everywhere in that region. The second is the emitting region completely defines the object of interest. In other words, there's no dead areas of significance. And the last one, which is a very safe bet, is that the speed of light is finite. So the light variation then is just a measure of the time it takes light to travel across the active surface. Multiplying the time by the speed of light gives the size of the emitting object. So I have some object here. It has a certain size. I don't know what it is. It's too far away to measure. But I'm going to assume that everything in here changes its light output at the same time. So if I'm looking at a brightness curve, the brightness curve. So as a light from A, as it gets brighter, it starts to increase. As we get more and more light throughout the whole thing, and finally when we get to B, all of it occurs, and it's at this new brightness. So the amount of time it takes here times the speed of light gives us the diameter of this object that's changing its brightness. Now, why do we get this activity in galaxies? All active galaxies have many features in common. So that suggests that there may be a single model to explain all of them. Such a model must explain how a small region can emit an extreme amount of energy over a broad range of wavelengths. The model must be unusual, since no ordinary star could be so luminous, nor could enough ordinary stars be packed into such a small volume. So our basic model is that we have a black hole about the size of the Earth with a gas accretion disk tens to hundreds of astronomical units across. As the gas in the accretion disk is drawn towards the black hole, it increases its temperature to millions of degrees Kelvin. Now, some of the gas is trapped by the magnetic field and ejected off at super high speeds on either side of this black hole. The accretion gas is replenished by nearby passing stars or material from collisions with another galaxy. So how do we get a massive black hole in the center of the galaxies? Well, we have a massive star in a densely populated core of galaxy explodes, and it forms a black hole, maybe a 5 solar mass black hole. And the black hole is going to continue to grow from the accretion of interstellar matter. And as the radius of the black hole increases, it makes capture of more material easier. Eventually, the black hole becomes large enough to swallow entire stars around it. And at this point, the growth of the black hole is exponential until equilibrium with all available materials stops the growth. So how do we know this? What's our observational proof? Well, the extremely high speeds of gas and stars at very small distances from the galactic center requires a huge mass to be there, on the order of millions of solar masses. Yet this mass emits no radiation of its own. All galaxies appear to have massive black holes at their centers. Now, not all galaxies are active, especially older ones. And this is because the central source of material that the black hole is gobbling up is diminished. And a one-to-one relationship of central black hole mass to bulge size could mean the black hole existed before the rest of the galaxy material surrounded it. Other theories of AGNs exist, but none is well accepted as the black hole model. Now, one of the things about quasars, because they are so far away, it allows the light from that quasar to be used as probes for any intervening material. Quasar absorption lines have very different Doppler shifts from the emission lines of the quasars themselves. It's an indicator of cool gas clouds between the quasar and Earth. And a quasar's light may also be affected by a gravitational lens. So, quasars are very bright and very far away, and as the light from a quasar passes by a massive object, it can be bent in much the same way that light is bent as it goes through a glass lens. The bending of light by gravity is a prediction of Einstein's general theory of relativity. And the bending light creates multiple quasar images and arcs that can be used to determine the mass of a massive object. So, for example, here we have a very distant galaxy. Behind it is a quasar. These four objects here are all the same object. And we can tell by the type of light that comes out, any fluctuations, it's always the same. So they're all the same. The quasar is actually behind the central galaxy, and what we're seeing as the light comes, it is bent around that galaxy and refocused down to where we can see it as four separate objects. So here we have the galaxy that's in between, here we have the quasar, and here we have Earth. So some of the light might try to go right through the galaxy, but quasars shine light in all different directions. So some of it's coming out here, and as it goes by this galaxy, it gets bent. And so as we see it, it appears to be here. Or another path might come here, and so we see it here. The quasar, there's only one of them is actually here, but we see multiple images due to the light bending around the galaxy, and we call that a gravitational lens.